Earthquakes are one of the most powerful and unpredictable natural events on Earth, capable of causing widespread destruction and altering landscapes in an instant. These sudden, often violent shaking of the ground result from the movement of tectonic plates, the large slabs of rock that make up the Earth's crust. Understanding how earthquakes happen involves exploring the complex interactions within the Earth's interior, particularly along faults where these tectonic plates meet. At the heart of an earthquake lies the concept of tectonic plate movement. The Earth's outer shell, or lithosphere, is divided into several major and minor tectonic plates that float on the semi-fluid asthenosphere beneath them. These plates are constantly in motion, albeit at a rate that is usually too slow to notice on a daily basis. However, the forces driving their movement, caused by the heat from the Earth's core, are immense. As these plates move, they interact in various ways. They can converge, diverge, or slide past one another. These interactions often occur along faults, which are fractures in the Earth's crust where significant displacement has occurred. An earthquake happens when stress that has built up along a fault line is suddenly released. As tectonic plates move, they do not slide smoothly past one another. Instead, they often get stuck due to friction, causing stress to accumulate over time. Eventually, this stress exceeds the strength of the rocks along the fault line, causing them to break or slip suddenly. This rapid release of energy generates seismic waves that travel through the Earth, causing the ground to shake. The point within the Earth where this release of energy occurs is called the focus, or hypocenter, while the point directly above it on the surface is known as the epicenter. The strongest shaking is typically felt near the epicenter, but seismic waves can travel great distances, affecting areas far from the original fault line. There are different types of seismic waves generated by an earthquake, each traveling through the Earth in distinct ways. The primary, or P waves, are the fastest and first to be detected by seismometers. These waves compress and expand the material they move through, much like sound waves traveling through air. Following P waves are secondary, or S waves, which move more slowly and cause the ground to move up and down or side to side. The combination of these waves, along with surface waves that travel along the Earth's exterior, creates the shaking motion felt during an earthquake. Surface waves are often the most destructive because they cause the ground to roll and undulate, leading to significant damage to buildings, infrastructure, and the landscape. The magnitude of an earthquake, which measures the amount of energy released, is typically reported using the Richter scale or the moment magnitude scale, MWW. While the Richter scale was widely used for many years, the moment magnitude scale is now more commonly employed because it provides a more accurate measure of larger earthquakes. Earthquake magnitudes can range from small, barely perceptible tremors to massive quakes capable of leveling cities. However, the magnitude alone does not determine the damage an earthquake can cause. Other factors, such as the depth of the earthquake's focus, the distance from the epicenter, the local geology, and the design of buildings and infrastructure, all play crucial roles in determining the overall impact. Earthquakes are most common along tectonic plate boundaries, particularly in regions known as subduction zones, where one plate is forced under another. The Pacific Ring of Fire, which encircles the Pacific Ocean, is a prime example of a highly seismically active area. It is home to numerous subduction zones and fault lines, making it prone to frequent and sometimes devastating earthquakes. However, earthquakes can also occur away from plate boundaries, in regions known as intraplate earthquakes, where stress within a tectonic plate causes a fault to slip. In addition to the immediate shaking, earthquakes can trigger secondary hazards such as tsunamis, landslides, and liquefaction. Tsunamis, which are large ocean waves generated by underwater earthquakes or landslides, can travel across entire ocean basins and cause catastrophic flooding when they reach shorelines. Landslides, which occur when the shaking causes unstable slopes to collapse, can bury communities and block rivers, leading to further hazards such as flooding. Liquefaction occurs when saturated, loose soils temporarily lose their strength and behave like a liquid due to intense shaking, causing buildings and other structures to sink or tilt. Predicting exactly when and where an earthquake will occur remains one of the great challenges in seismology. While scientists have made significant strides in understanding the conditions that lead to earthquakes and in identifying areas at risk, the precise timing of an earthquake is difficult to determine. However, advancements in early warning systems, which detect the initial P waves of an earthquake and send alerts before the more damaging S waves arrive, have helped reduce the impact of earthquakes in some regions, by giving people and systems crucial seconds to take protective actions. In summary, earthquakes are a powerful manifestation of the dynamic forces at work within the Earth. They are the result of the immense pressures and movements within the planet's crust, leading to the sudden release of energy that shakes the ground. While they are natural events that cannot be prevented, understanding how they happen and preparing for their effects are vital steps in mitigating their impact on human life and infrastructure. As our knowledge of earthquakes continues to grow, so too does our ability to coexist with these powerful natural forces.